Let's see what are the conditions that is specified in IS 13920. In this code is for ductile detailing of RCC structure subjected to seismic forces. Actually, I already stated that a ductile detailing is necessary even if the earthquake is not occurred or not considered. Wind load may be higher than the design load of earthquake, but actual earthquake load is 10 times greater than the design load. Hence, the ductile detailing is necessary to avoid the failure. The meaning of inducing some ductile property to the structure is we are trying to induce some ductile property to the concrete instead of its stiffness or brittleness. If the building is ductile, means all the masses in the building will have the same deformation. The ductility increases linearly with increase of shear strength carried by the concrete for small value of axial compressive stress. With the increase of ultimate strain of concrete, ductility factor is increased. Hence, conforming to concrete is more ductile. Ductility increases with increase in concrete strength actually, but increase in yield strength of steel decrease with ductility. The lateral reinforcement tends to improve its ductility by preventing the shear failure, and the bond failure and anchorage failure is sudden and brittle. The special attention may be given to these details. Okay, let's see what is earthquake resistant design. The acceptable response level of the structure under design earthquake. The designer should exercise some degree of control on magnitude and distribution of stiffness, mass and relative strength of member and their ductility to achieve desired result. Seismic design criteria as per IS 1893. Earthquake design behavior controlling parameters are different according to the earthquake intensity. Sometimes the earthquake intensity is minor, then the desired behavior is no damage to non-structural component. The controlling parameters are the control deflection by providing stiffness. In case of moderate earthquake, no significant structural damage, minor cracks in beam and columns, and the response should be predominantly elastic. That is the desired behavior. Then let's see what are the controlling parameters. Avoid yielding of members or permanent damage by providing strength. In case of severe and catastrophic earthquake, no collapse of the system which could cause loss of life. That is the desired behavior. What is the controlling parameter? Allow structure to enter into inelastic range and absorb energy by providing ductility. If elastic strength of the structural elements exceeds the greatest imposed load upon that structure, there can be no significant damage. In severe earthquake, some of the resisting element will be loaded to their full strength. If they are brittle, they will fail, throwing their share of load on the remaining elements. If they are ductile, they can continue to participate in resisting the lateral forces up to their full strength after they yield. Ductility. A ductile material is one that can undergo large strains while resisting loads. Ductility implies the ability to sustain significant inelastic deformation prior to collapse. Brittle material is one that fails suddenly upon attaining its maximum load. You see, this is the within the elastic limit. This is the elastic limit. Within the elastic limit, the material is brittle. Here, then deformation after the elastic limit, it is ductile properties. It exhibit ductile properties. This is some technical terms that is relating to the material in its stress strain curve relating to ductility. Then see, what is the significance of ductility? It can be expected to adapt to unexpected overloads, impact and structural movements due to foundation settlement and volume changes. Occupants will have sufficient warning of the impending failure, thus reducing the probability of loss of life in the event of collapse. All joints and splices must be able to withstand forces and deformations corresponding to yielding of the reinforcement. Design for ductility. Structural layout should be simple and regular. Amount of tension reinforcement in beams should be restricted and more compression reinforcement should be provided. Beams and columns in reinforced concrete frame should be designed in such a manner that inelasticity is confined to beams only and columns should remain elastic. To ensure that moment capacities of column at the beam column joint should be greater than the moment capacities of the beam along each principal plane for design axial load. The shear reinforcement should be adequate to ensure that strength in shear exceed the strength in flexure and thus prevent a non-ductile shear failure before the fully reversible flexural strength of member has been developed. In beams, at least 2 bars. It is very important in the perspective, from the perspective of earthquake, at least 2 bars should be provided continuously both at top and bottom. The positive moment resistance at face of the joint should not be less than 1/2 of the negative moment resistance provided at that face of the joint. Neither the negative or positive resistance at any section along the member length should be less than 1/4 of the moment resistance provided at the face of the either joint. You see, it's a typical beam reinforcement in the consideration of ductile detailing. You see, this is the way you actually, I think you will be familiar how to provide the reinforcement in a beam. In bottom there will be a tension reinforcement, at top there will be stirrup holder. If necessary, you should provide some positive moment reinforcement at near to the support. In vertical bars, you can see here it is the stirrups, and the importance, the relevance points relating to this one: the spacing of hoop over the length of 2D at either end of the beam shall not exceed d/4. What is, you see, this is the total effective depth D, small letter D, you can see here effective length from top to center to its reinforcement, bottom reinforcement, it is effective depth. The 2 times of D, what is the length? 2D, that much D is the space for shear reinforcement, actually the stirrup. That spacing should not be greater than D by 4. Here the spacing should not be greater than D by 4 at either end near to the support, D by 4. Why? Because at this area actually the shear force will be very high. Shear force will be high. The shear reinforcement has to be provided in such a way that in this 2D, within 2D length, the spacing should be minimum. Okay, spacing should be minimum because of to resist maximum shear stress. Okay. 8 times of the diameter of the smallest longitudinal bar need not be less than 100 mm. 8 times the diameter of the smallest longitudinal bar need not be less than 100 mm. Elsewhere, the beam shall have the vertical hoops at spacing not exceeding D by 2. Elsewhere, the beam shall have the vertical hoop at spacing not exceeding D by 2. In with the remaining space, the hoop, the spacing should not be less than D by 2. In this first from support to support is the total span. The first 2D means the 2 times of dia, that much length is the shear region from the either support. The remaining portion from less than the hoop spacing, actually in this area the spacing should not be greater than D by 2. And one more point is, this is the face of column. From here the first vertical reinforcement means first stirrup should not be greater than 50 mm. In column, the factored axial stress shall not exceed 0.1 FCK. Minimum dimension of member is 200 mm. If center to center distance of beam exceeds 5 meter or unsupported length of column exceed 4 meter, then minimum dimension should have 300 mm. The ratio of shortest to perpendicular dimension shall not be less than 0.4. You can see all these things in IS 13920. The special confining reinforcement shall be provided above and below the beam connections in a length of column at each end which is largest of the following: 1/6 of the clear height of the column, larger dimension of the column for 50 mm. When a column terminates into a footing, the special confining reinforcement shall be extend at least 300 mm into footing, like this. This is the special confining reinforcement should be extend to footing. Okay, this much area is 300 mm, like this. This is an example for column beam joint. Actually, you need to study this drawing in detail. I will explain later. The spacing of hoop used as a special confining reinforcement shall not exceed 1/4 of the minimum member dimension, need not be less than 75 mm nor more than 100 mm. For further information, you can see the clause 7.4.6, 7.4.7 in IS 13920. Here is the development length in tension LD. dB is the dia of the bar. All the things here, the column, beam, what should be the total development length in a that has to be provided. Sorry, provided it has to be extended to column. All the things will be given here. Lap splices in beam. Not more than 50% of the bars shall be spliced at one section. The longitudinal bars shall be spliced only if hoops are provided over the entire splice length at a spacing not exceeding 150 mm. The lap length shall not be less than the bar development length in tension. Lap splicers shall not be provided within a distance of 2D from the joint face, or within joint within a quarter length of the member where flexural yielding may generally occur under the effect of earthquake phase. Use of welded splice and mechanical connection may also be made as per IS 456. This is lap splice beam. At lap splice beam, the spacing should not be greater than 150 mm at the where splicing is given. Web reinforcement consists of vertical hoops enclosed, the stirrups having 135 degree hook with a 10 mm diameter extension but not less than 75 mm at each end. Also use stirrups with a 135 degree hook and 10 times of diameter of bar extension at each end embedded in confined core and a cross tie. Minimum diameter of bar forming hoop is 6 mm but beam clear span greater than 5 meter, minimum bar diameter is 8 mm. Shear force to be resisted by vertical hoop is maximum calculated factored shear force and shear given below. Let's see, this is the way actually you are calculating the shear. Both end is fixed in such case. This is theoretical part. I think you are already familiar with these equations, all the things. You see, this is the cross section of a beam or a column. Actually, for reinforcement are provided here. Stirrup is provided here. This is the hoop, or this is the stirrup. What is the length of this stirrup hook? It should not be less than 10 times of dia of bar, or it should be greater than or equal to 75 mm, 7.5 centimeter, or 10 times. Or otherwise you can provide U stirrup and cross tie. You can provide like this one. This is two, instead of providing a complete hoop, you can provide as a two parts. One part is like this one, other part is like this is cross tie. Okay, and the length of this hook means this point to length from this point to this point. Actually, it should not be less than 10 D. And the distance, this is the core of concrete. It should not be less than or equal to 300 mm in B, and other side also should not be less than or equal to 300 mm. H shall be larger than HC and BC. The total overall size, minimum size should be 300 mm, and the hoop edge hook length should not be less than 10 dia. This is the way we providing the cross tie. Actually, we already discussed that the length of the hook means the hook extension is 10D here. This is the dia of the bar, and HSE means a face. One is at least one face should be greater than 300 mm. Minimum lateral dimension should be 300 mm. And cross tie he is providing like this. This is the extension here. It is enlarged figure is given how this cross tie is provided. It is the longitudinal bar is provided here, this cross section. This is the main bar is provided. Then lateral tie is coming to this direction in such a way that you need to provide the cross tie. You see here a cantilever beam. Actually, some practice are going on in our construction site. This is a beam. It is continuous beam. Actually, this portion is cantilever portion. This beam cantilever portion. This is the main beam. As an extension to this beam, a cantilever portion is extended to up to this point. Because of the amount of shear force is higher at support, near to the support, and actually this column, this beam size is reducing from larger depth to lower depth. Actually, at this point, actually there is a chance to have some cracks due to some shear. So at this shear area where the shear force is maximum, at that space, at that region, the stirrup holder should be provided very closer. If this is the incorrect layout of reinforcement, all the ties, lateral ties are provided at larger spacing, at equal larger spacing, but very near to such case, very near to the support, you need to provide such lateral ties very closer. Okay, here at what extent you need to provide this lateral ties very closer is from support L by D to from either side. Okay, L by D2. Because there is more chance to have a crack here like this one, a red mark. So as it is sagging here, actually it is another case. Here here is a column, here is a column, and here is a column, and as it is a prismatic beam, means all the cross section have different cross section. So it is non-prismatic. Prismatic means the length of the beam having the same cross section. Non-prismatic beam means the beam having the different cross section. At this region, the beam depth is different. Hence, there is a chance to have some crack like this one. To resist here, the stirrup lateral shear reinforcement means the stirrups should be provided closer here. In grid beam, one beam carrying and secondary beam. If it's such points, actually in this point, this is the main beam, there is a longitudinal beam also coming to here. Actually this beam is secondary beam. It is supported by the main beam. Okay, it is this secondary beam is perpendicular to this main beam like this one. Okay, in such cases, actually the secondary beam inducing a point load to this main beam. As the point load is inducing to this main beam, actually the shear force will be higher than the other region. In such cases, you need to provide the lateral ties closer, okay, more closer. It is comparing to other spacing like this one, 1.5 times D from either side. It is the close rings should be provided. And this is the way normally we providing the reinforcement in a slab like this one. Actually here it is the maximum reinforcement, 100% reinforcement is provided here at the middle of the span, because maximum bending moment will be here. At support, negative bending moment will be here. So we needed to provide some tensile reinforcement at support at the top, because hogging moment is here. So we are doing is alternative bars is bending up to ensure the reinforcement, minimum percentage of reinforcement at support. So alternative bars is bending up to top. So here will be the 100% of reinforcement, here will be the 100% of reinforcement. So this is the way we are doing the bending up. Actually 1/4 of the span is the length, that is from center to the column or support. From center to the support, you taking 1/4 of the span. From that point you starting the bending up. This is the way normally we are adopting the bending up process, but it is not correct. Actually the correct way is, what is the total effective depth, that is D. 1.5 times of D you need to bend up, from here to bend up at an angle of 45 degree like this one, T. Okay, and here is the also you need to provide an additional bending up like this one, because of there is chance to have some cracks due to some shear force. From one point you have already marked 1.5 times of D here. From here you need to provide additional bending up like this one. It is very suitable for your site to withstand the shear force and to prevent the shear cracks. So there is more chance to have a cracks after this portion. So to prevent to prevent the effect of the shear force effectively, this is the correct way to provide the reinforcement. So from support, 1.5 times of D you need to provide the bending up like this one. From that point, D by 2 plus D by 2 cot theta. Theta is nothing but the angle of bending up. Okay, that much length also you need to provide an additional bending up and alternative bars. Okay, it will be very useful. We can actually, this type of reinforcement layout very useful to prevent the cracks due to shear force. In case of continuous beam, this is the incorrect method of reinforcement layout. Normally from span by 4 is this is the distance span by 4. From that end you started the bending up the reinforcement from the either side. You see, this is the way the bottom bar is here bending up to top at up to the span by 4 length like this one. You watch carefully how which reinforcement is, then the reinforcement is started from here, then come to here, then come to here, then come to here, then gone up, bended up to top, and it is extended to the next span up to span by 4. Okay, likewise the bottom bar is bended up to, and it is embedded to like this one. This is the way normally we are providing the reinforcement in continuous beam. Instead, we can improve like this one, and we can the span by, instead of span by 4, what is the total depth of effective depth? Then 1.5 times of d you need to provide this bending up like this one, 1.5 d like this one, 1.5 d like this one. This is the way, actually this is the correct method to provide the bending up reinforcement. This is the correct way. Okay. Sometimes now these days the bending up of bars is not doing in our site. Instead, we providing the additional reinforcement, or we providing the reinforcement by we applying some this process by curtailment. So if we are curtail the reinforcement, this is the correct method, actually the reinforcement is provided. You see, instead of 0.1 L1, if it is L1 is the spacing first span, center to spender span, L2 is the second span. You see, L1 is the first span, center to center span. The curtailment you need to end, means the main bar, first one main bar is running throughout the beam. The second bar is actually can be curtailed up to this portion of 0.1 L1. The second bar, alternative bar, is curtailed at 0.1 L1 at either end. Here 0.1, it is at this end the beam is not continuous. But at this end this beam is continuous. Hence, at this center, from center of the support, you need to curtail the alternative bars at 0.15 L1. At other side, you need to curtail the reinforcement 0.15 L2, because at this from this support the beam is continuous to either side, and alternate bars are curtailed at bottom like this one. And additionally, the intention of the curtailment is to bend up this bar. Actually, if you are not curtailed, you need to bend up this bar to top to ensure the 100% reinforcement at support. For that purpose, you need to provide the bending up. Instead of bending up, you need to provide the reinforcement at an extent of L1 by 4 length. At 100% reinforcement will be here. Actually, we are bending up the reinforcement alternatively. Instead of bending up, you are providing the reinforcement by curtailment. At support, the total length of the bars that you need to provide is L1 by 4. L1 is nothing but center to center distance of first span. Okay, L1 by 4. Here L1 by 4 plus L2 by 4 here. Here this from at this point, the negative bending moment, to resist the negative bending moment, you need to extend the reinforcement at support up to L1 by 4. Towards L2 span, you need to extend it L2 by 4 like this. This is the correct way you need to follow the reinforcement in column beam junction. Okay, if you are not doing the bending up, instead you can provide the extra bar like this one. This is the correct method. Okay, if it is if you are doing like this one, here it is the chance to have some cracks very near to the beams, means beams support, very near to the support. There is a chance to have cracks like this one. This is the incorrect method. Actually, don't follow this type of reinforcement alignment. This is the correct method to provide the reinforcement in column beam junction. Sometimes you need to provide non-prismatic section of beam like this one. Sometimes you need to provide some sunken slabs beams like this one. So you need to care. Actually, this is the incorrect method of providing the reinforcement. Here the bottom reinforcement is provided like this one. It is bending up like this one. Continuity is going up like this one. This is the incorrect method. Actually, this is the weaker point. Actually, this point is a weaker point. There is a chance to have some crack here like this one, yellow color marked as. This is incorrect method of reinforcement layout. Instead, we can provide the reinforcement in this junction like this one. The bottom reinforcement is started to here, and it is bending up top, and it is a loop is there, and it is extended to here like this one. And the top reinforcement is provided here, and it is looped here, and it is bending up towards top, and it's like this one. This is the correct method providing the reinforcement to avoid the cracks and additional the stress behavior is different unlike the continuous beam. So to avoid such complexities, so you can provide the reinforcement like this one. The main reinforcement can provide like this one. It is better way to provide. Actually, it will be provided as a stirrups as well as a beam. Actually, this portion will be act as a beam or as well as a stirrup also. The cantilever beam projecting from the column. This is the incorrect method. Actually, the method of providing the reinforcement. Actually, you see here a bottom reinforcement is provided here. At the top, one reinforcement is provided and is bent up downward to the column, and additional and it is actually this bar is intended to bending up. Actually, the bottom bar intended to bend up towards this direction and it to continue to this direction. Instead that the bottom reinforcement is extended to here, and an additional bar is provided like this one. This is a wrong one. Actually, this is not correct. The bottom reinforcement is correct, provided like this one, and the top reinforcement also need to provide like this one. The top reinforcement, because unlike the normal slab, it is a beam is cantilever beam, hence the tension reinforcement is normally provided at top. So the main reinforcement are at top. It should not be less than 0.5 times of AST. So this reinforcement has to be provided like this, and we have to make sure that this reinforcement has extended to the column. Here see the top reinforcement is not extended to the column up to the, it is only up to the beam bottom, but this reinforcement has to be extended certain extent up to the column. And also normally we this bottom bar is needed to bending up to top. Actually that bar also need to extended to the column. This is the correct way providing the reinforcement. Then only this junction will be sufficient, will attain the sufficient strong. Otherwise what will be happen is the reinforcement inside the column, the reinforcement inside the beam will not be won't have sufficient bond to the strong, will not have sufficient bonding strength. So the reinforcement inside the beam is extended to the column is very necessary to ensure the column this junction strength. Okay. Sometimes you need to work in such a situation of sloping beam. Sometimes sloped roof need to provide. Normally this is always the laborers committing the mistake. The bottom reinforcement is starting from here, and when it is reaches to, it is not extending to like this here direction, and it is bending to downward direction. Likewise, the top reinforcement also started to top, and it is bending to downward direction. It is not correct actually. So instead, this is the correct method. We providing the reinforcement in sloped slab is the bottom reinforcement is when it reaches this point, it is extended to top of the slab. Likewise, from here it is extended to top, and the top reinforcement also like this one, and an additional bar means this cracks will be, there is a chance to have some cracks, so this portion will be sufficiently strong. Okay, the bottom bar has to be extended, and an additional bar also needed to be provided here to bend up like this one. You see, this bar is bending up to, additional bar is provided here to like this one. A development length bar has to be provided here like this one. This is the correct method for providing the reinforcement at a sloping beam. A haunch beams, actually the haunch beam like this one, there is a column, actually the beam depth is more than the depth of beam at support, at the middle portion. Here the depth of the beam is like this one to like this one. This is the this type of beam is normally called the haunch beam. In such situation, normally the bottom reinforcement is continuous. Actually, it's not correct. This is the correct method. From column, the bottom reinforcement of the beam has to be extended to column like this. This is the development length. That much length has to be extended to the column here. So this bottom reinforcement is starting from the outside of the column. It is bending like this one. You see, this reinforcement is extended to top. Okay. Likewise, here the bottom reinforcement is starting from outer face of the column, and it is extending to like this one, and an additional horizontal bar is also provided. Okay, and a top reinforcement also, stirrup holder is already there. That reinforcement, that main stirrup holder also extending towards to the column. Actually, this portion, this triangular portion of this beam also a part of column. Okay, so this is the correct way that we are providing the reinforcement. Stresses at corners. Actually, this is the way having some stresses at corners. At the top, compression here, at the top compression, at the bottom tension, at the bottom tension. Sometimes the angle of slabs sometimes like this one, sometimes like this one. So there is a chance to have some cracks like this one because of the resultant tensile stress for across the corner. So to avoid this one, we need to provide the reinforcement from this extent. Actually, this from bottom reinforcement has to be extended to upward direction. Okay, and the bottom reinforcement has to be extended to this direction. This is very important thing. Shear and torsion reinforcement in beam. Actually, the skin reinforcement 10 mm dia is required when the depth is exceed 450 mm. 0.1% of the web reinforcement 0.1 percentage of web area distributed equally on 2. This is the way when the stirrups are taken round. Outmost bar spacing should be less than or equal to like this one. The minimum percentage of steel BD to control the deflection like this one. I think this is not much important for you.